Today we're going to talk about 5-5, inequalities in one triangle. And we're actually going to start it off with some math humor today. What do you call a prisoner's poem? A converse! Okay, we should get back to math. That wasn't funny. Okay, this entire section, 5-5, talks about, it says that the angles and sides in a triangle are related by their positions. These are summed up in two theorems. It's okay if you don't understand them right now. I'll summarize them in just a second. Our first theorem is theorem 5-5-1, and it says that in a triangle, the larger angle is opposite the larger side. And that's all it says. And again, we'll look at this in just a second. Our next theorem, 5-5-2, says that in a triangle, the larger side is opposite the larger angle. These two theorems look very related. We only really have a few words that are interchanged, and that is because these theorems are incredibly similar. To summarize, I'll summarize below and what these two basically are saying. To summarize, in a triangle, the sides and angles across from each other are arranged by size. What that means is that the biggest side is across from the biggest angle. The smallest side is across from the smallest angle, and the medium side with the medium angle. If we had a triangle, triangle ABC with side lengths of 12, 5, and 13, and what we want to do is if we wanted to go through and rank from largest to smallest the size of the angles, we have everything that we need to do this. What we look for, since we're looking for largest, look for the largest side, which is 13. The largest angle will be directly across. See how B and 13 make a pair? So therefore, angle B is our largest. Then we look for our medium. The next biggest would be 12, and 12 is the furthest away from C. It's right across from each other. So next is angle C. And lastly, we use our smallest, and of course it's going to be angle A, but why? Our smallest side is 5, and across from it is angle A. And so therefore, our smallest angle would be angle A. On the flip side, if we now wanted to sort the sides, and we didn't know what the side lengths were, we knew the angle measures, we could actually do this now. We can do this one as well. So we're going to go along here. Let's look at all of our angles. I see a 90-degree angle, so we have a right angle. The 53, which is great, but we don't know up here. So we do want to find that out. And how we do that? Well, how many degrees are in a triangle? 180. So we have a right angle, so we need to subtract 90 degrees here, and that gives us 90. And then we know a 53, so we're going to subtract 53 as well. And let's see, that gives us a 7, and that gives us a 37. Meaning that this top angle here is 37 degrees. So now we have all the information we need to sort the sides. And let's do it from largest to smallest. We have a 90-degree angle, so the side directly across would be over here. And so that would be segment AC. And then we look for our next biggest, which is 53, and we go directly across, which would be that side over here. So that would be side AB, and then for the same reasoning, our smallest side would be BC. Now we are moving on to a new theorem. As I labeled, it's a new idea, new theorem. This stuff here is not really related to the past two theorems we were doing. Although it's not as it's not any more crazy. Just kind of get that out of your mind that they are unrelated ideas. This theorem is formed on the idea of although a triangle is formed with three segments, there's three sides to a triangle, not every set of segments will make a triangle. Consider, for example, these three segments. I drew them here. Try to make a triangle out of these three segments. This one might be kind of obvious. I mean, there would be no way to do it. You can't take these small segments and lay them any way to touch each other, and therefore you would never make a triangle. A triangle does have to have the closed sides, So that these three segments would never form a triangle. Maybe a more concrete example. We're going to try to form a triangle with lengths 6, 2, and 3. We have a segment of length 6, a segment of length 3, and this one will be the 2. So I'm going to move this 2 over. And as you can see, the 3 and the 2 don't touch. Let's see if I can move the 3. I can try to turn the 3 around any way I want. Oops. Try to twist this segment. I can try to twist this whole guy. I can connect the 2 and the 3. But the point is that these will never touch. I can never make a triangle out of these segments. And the next theorem will actually tell us why. The reason why that triangle would never form is because we have this theorem 5-5-3. It says the sum of any side lengths of a triangle is greater than the third side length. What exactly does this mean? If we have a triangle ABC, we have a triangle formed, this theorem tells us that we can say that AB plus BC will be greater than AC. Basically that AB plus BC, if we add these two lengths up, it will be bigger than AC. And then we can just go around the rest of the triangle and we can say the length of BC plus the length of AC will be greater than the last side, which is AB. And lastly, the length of AB plus the length of AC will be greater than the length of BC. So if you have a triangle, you can add any two sides you want, and they will be longer than the third side. So why exactly can we not form a triangle with segment lengths of 6, 2, and 3? Well, let's take a peek. The reason why that does not work. Let's add up 6 plus 2. Those are two sides of the triangle. Is it greater than 3? Yes, it is. 6 plus 2 is 8, which is greater than 3. Okay? Now let's add up 6 plus 3. And this has to be greater than 2. Is that true? Yes, it is. So that's 2 criteria. Now the last one. You need to add up 2 plus 3. Is this greater than 6? No, it is not. And that is the reason why you cannot form a triangle with these side lengths. Is that the 6 is larger than the 2 plus 3, which is 5. So the question is, how can I check if a triangle can be formed from any given side lengths without having to look at a picture or anything? All we have to do is look at some numbers. It's actually a really simple process. You just add up the two shortest sides and you say, is it larger than the third side? If yes, then a triangle can form, and if no, no triangle can be formed. So a quick example here says, can a triangle be formed from lengths 6.2, 7, and 9? And again, we don't need to look at a picture. All we have to do is add up the two shortest sides, check to see it's longer than the third side. So two shortest sides would be 6.2 and 7. So we add up 6.2 plus 7. This will give us 13.2. Is 13.2 bigger than our last side of 9? Yes, it is. So since 13.2 is greater than 9, our answer is a big ol' yes. And the reason for this is by theorem 5-5-3, which is the triangle inequality theorem. Now, last example, this one is important. Can a triangle be formed by lengths 8, 13, and 21? Do the same process. Add up the two shortest sides. 8 and 13. So 13 plus 8 gives us 21. Is 21 greater than 21? Well, no, 21 is not greater than 21. And so therefore, we say no. And again, this is by our triangle inequality theorem, which is 5-5-3. 21 is not greater than 21. The sum is not greater than our last side. Both of these concepts are not too crazy. Hope you guys understood them. If not, make sure you mark down any questions you have in your notebook and make sure you ask in class. Have a great day.